coming up next week, so do remember about that. Okay, so back to the interrupts thing. So we talked a little bit about USB versus PCM-CIA. I have an old keyboard on here from 1994 that uses the PCM-CIA interface. So when we push a key to do something like switch tabs, if I can push the right keys, it interrupts the CPU every time I push a key. So this does slow down productivity just a little bit. If you have a computer busy doing something and you're pushing keys on this keyboard, it has to interrupt it. Some of you have kids and have tried to work while kids want something, and you get a steady stream of interrupts. After the interrupt, it takes a moment to get back into the groove and start working on whatever you're working on again. Same thing with the CPU. Now, it's gotten better as of late. It used to be at a 1 core. This one I'm carrying around here is 3. The computer's in a room of 6. And so the more we get performance by spreading this into more cores, the less the interrupts are actually a problem, because you're only interrupting 1 out of maybe 6 processors instead of the 1 processor that runs everything. And so that can help quite a bit. I'll put this note on here, how often. Let's see, how often? Okay, go to the computer here in the room. And so this is a chart that's pretty hard to read, actually, at this font size. This is showing the number of interrupts that are handled by each of the CPUs. The reason it's hard to read is the chart wraps around there. It is CPU number 11 right over on that side. So let's go to my office computer real quick. The advantage of the office computer, as opposed to this one has 6 cores. They look like 12 of the operating system because they're each duplicated with hyperthreading. The one in my office only has 4, so they look like 8. So if we look at this chart, it is formatted much more correctly for our screen. Okay, so up at this top, you have an entry for each of the apparent 8 CPUs, which are actually only 4 real cores in the system. And you can see counts for how often each of these interrupts has happened. So over on the other side here, we have an explanation of these, and unfortunately it wraps over to there. We could decrease the font size and make it so nobody in the back of the room can see, but I'm not sure that's an upgrade. There's quite a variety of these. So a lot of these are set up with the number right in here, and there's usually some sort of commentary on what the number is. Now, back in the old days, anybody who's built a computer in the 90s can remember this process, but it's kind of gone away. We used to put in a type of card called an ISA card, and I don't have anything quite as old as an ISA card. This is an AGP. This is 2 generations later, but it's a different set of pins under here and a different interface internally. Has less pins. And part of the difference with the interface is these days, your BIOS, basic input output system on the motherboard, will go ahead and figure out what's in the machine and assign interrupts when you turn it on. It used to be that that wouldn't happen, and so the card would have either switches or jumpers, which is like a manual switch where you put a little tiny hat thing to connect 2 wires on it. It used to be they had those, and you configure your card to be on a particular interrupt. And so you make sure none of these extra cards in the CPU have the same interrupt as each other. And it can be kind of a headache, especially if you had a lot of them. In some cases, certain cards could share interrupts, and a lot of times that was essential, but could lead to other difficulties. Anyway, those days are gone. These days we have the BIOS assigning interrupts. A lot of them are just numbered here. Some of them aren't. And so over here on this far side, you can see the numbers for everything that has one, and then some special ones that don't. So then over here, we have to count how many times each of these interrupts have been handled by the CPU. This timer here has apparently had issued 29 interrupts. It's probably not used very much. Those 29 may have come from testing the blink keyboard light blinking kernel module the other day. So it's not a very super common one. We have this I-8042. Let me pull up this computer's table. I don't think I want to split that. I think I just want a separate window. Okay, so we'll carefully look at line 1 here, which is going to wrap over. You can see this 8042 doesn't have nearly as many interrupts on this. You got 35 and then 529. So let's go ahead and do this again. Exact same thing, running the same command. And you can see we're up at 35,545. I'm pretty sure we were less than that. Yeah, 529. We're continuing to issue interrupts for that particular one. So I'm going to carefully run this command without touching the keyboard. We'll take it right here, copy it, paste it. You know, I think I'm stuck because oh no, it ran. Okay. So look at the top, 552. So it's received a little bit less advancement there this time. So demystifying here, this is the interrupt for my keyboard. Whenever I push a key, it interrupts the CPU and adds 1 to that count. So when I carefully did it with the mouse, we only saw an advance of 1. The advance of 1 probably came after I ran the command from letting up the enter button after running it the previous time, since I was careful to use the mouse. So if we wanted to not issue that interrupt, all I actually need is a USB keyboard, and we can prevent it. We have a USB keyboard. It's back here somewhere. There we go. This particular keyboard's in the closet because it was on that machine, and somebody noted that the space bar occasionally sticks. So you noted that the space bar sometimes sticks. Okay, so I got a USB keyboard right here. Put it right there. I'll plug it in. The computer will be happy to have 2 keyboards. Everyone knows 2 is better than 1, right? Okay, we're connected. So we're not connected. There's no lights. We'll try it on USB port on the
It works just fine, Seth.
Yeah. Oh, it did?
Yeah.
Oh,
no lights didn't come on.
None of the things are on. Okay, that's fine. Okay, well anyway, yes, it worked just fine. Okay, so we'll take this proc interrupts and we'll type it into head. So we only see the first few lines, that way we can see the end. And so you can see the 560 there is not changing when I run it again. Try this keyboard. There it goes. On its way up. Okay, so interrupt number 1, it's happening whenever the PCMCIA keyboard does something. USB one doesn't factor in that. So there's so most of these have some sort of purpose like that, and that's a good example one. Okay, let me get back to notes here, see what I'm supposed to talk about. Okay, so different devices, different interrupt numbers. Interrupts interrupt the processor, sure. Okay, finishing the interrupt handler. So at some point, the kernel has to handle the interrupt, and typically these are handled as fast as you possibly can. The reason is, when an interrupt handler is happening and handling the interruption, nothing else can happen on that processor. And in the single core days, that meant on that computer. So you didn't want to have a long interrupt handler since it makes it take quite a long time. So for example, I worked on a driver for a capture card. It would capture audio waveforms, and it would issue an interrupt whenever something happened that needed to be captured. It would give a steady stream of these. They happened at a certain frequency when you were sampling, or if you weren't sampling, then you get them otherwise. Anyway, an interrupt would come in, and so there were 2 things to be done. One was taking the audio sample and actually going and saving it and squirreling it away somewhere. And then part of it was preparing the audio sample to be handed to the user so they can see what was going on. That second part would happen later. So we'd record everything that absolutely had to be done right then in the interrupt handler, and then stop and schedule the rest of it for later, whenever we get around to it, which is often how interrupts go. If you're working and somebody comes and says, oh, you know, I'd really like it if you did your taxes. You know, you probably go away and do it again in a few months, right? So you schedule something for later. You don't do it immediately because there might be some other pressing matter to attend to. Anyway, same kind of thing happens on the CPU. Not quite as critical now that we got more than one processor, but still the general practice here. We could set a timer to do stuff later, like with the Blink kernel module. Okay, so requesting an IRQ. Let me show you an example here. And it's on a software. Okay, nettrap.c. So this is a kernel module that monitors computers for network traffic, or you can monitor any other interrupt. It starts looking for an interrupt. It installs this interrupt handler, and then all it does is count how many times this interrupt happened. So module init here is set to start things. So that's the function it first runs when this module is inserted. So when the module is inserted, we go ahead and request IRQ, and so we request a particular IRQ, and we identify ourselves as netmon. Then we print out if we received an error, if everything didn't work right. And then we create this file in the proc file system called netmon, where we can look at what's happened later. That'll be, we'll have a read operation for that up here that tells us the total calls. Now the IRQ handler we install. You can install an IRQ handler for, same IRQ handler for more than one IRQ if you want. So it has a identifier here to tell you which IRQ you just received. You can also have a device ID. This resolves to a structure that tells you a lot about the device that generated it. And so it can be cast to an appropriate type, and we can do things with it from there. And then we've got the set of registers. So we don't have to do this ourselves. But remember, when the CPU is interrupted, it was doing something. Remember from architecture class, you put things in registers, right?
Yes.
Yeah. So there's certain contents of all the registers in a CPU at the moment it gets interrupted. And in order to set it back to what it was doing later, these have to be restored. The kernel has mechanisms for this. You don't have to do it in your interrupt handler. You can find out what the interrupts are in case you need it, or the registers are containing in case you needed them, but you don't actually have to do anything with it. So then we return a value here. In this case, we're returning this special constant value IRQ handled that just says, no, we did what we did and we're done with it. Now, that doesn't necessarily disable other IRQ handlers. We have this one set down here, kind of skipped over this function right here, which I think is actually missing something. We'll have to fill that in. Anyway. It takes this parameter here, IRQF shared. So we're actually going to be sharing this interrupt with whatever other interrupt handlers were registered. And so this is part of how you share an interrupt between different devices. If you install a number of interrupt handlers and they're all set IRQF shared, then they'll all be run when that particular interrupt is received. But when it is, since you can figure out what device you were on using dev ID up here, if it's not your interrupt, you can just go ahead and return and not do anything more. So this is how we get away with having less of these interrupt numbers. Now, there's gotten to be more and more interrupt lines on computers, and so actually sharing them between different devices has taken on a little bit different nature. It used to be that you'd share because you just didn't have enough interrupt numbers. And these days, you tend to share because you have a whole bunch of stuff plugged into the USB bus, and the USB controller has one particular interrupt that then is shared between all the devices plugged into it. So when the USB controller says it's pulling, it'll come up with anything that any of the devices have done, and that'll be returned for that particular interrupt. So if you have a USB device, when you get an interrupt from the USB controller, it could have to do with your device, or it might not. And so that's one thing that would have to be straightened out right there. Okay. So you probably recognize this last one as a function pointer of some sort. We got IRQ handler here as a function being cast to a void star, very similar to project 1 and the way the list of functions was passed. We take some complicated type and pass as a void star, and off it goes. So that's the use of request IRQ right there, and set up. Okay, this last part of the total calls, this mechanism is pretty straightforward. It looks a lot like what you see in other C programs. We have that size up there, count, and so T count up here is the count of interrupts that we've received so far, and so then this message here is filled out using total calls. And then this will be a 64-bit unsigned integer, like this one up here. And then we have T count, which is that one. And so it'll fill out the contents of message here. Then we're going to copy message into buff right there, which is this thing up here. So buff is the memory that the user has allocated for us to go ahead and put this message in when it called read. I realize I kind of talked through read before, but since everybody's working on it right now, it's project 2. We'll go through it in detail again. Okay, so with read, the user has probably run something like this. And so when they run this function up here, they're asked to give some sort of buffer in order to put the results of whatever we've read from whatever file we're going to read from. So that buff there comes right through right here. Doesn't have to be named the same thing, but I did. Once that's in here, we can copy stuff to it. Now, there's another function besides str cpy that's attempting to use here, and that's copy to user, which is designed for copying between kernel space and user space. In a lot of cases, it'll work just fine, whichever one you want to use. But keep in mind that that one's out there when you see examples of this stuff. Okay, so that's the module there. Okay. So we want to grab this and try to build it for this machine that we're at right now. So I've got this kernel module directory, and I've been occasionally getting questions on how to build modules, usually from somebody trying to build one for project 2. Okay, so we have this make file right here, and this one's set to build blink.o. So file names here. We've got a bunch of things that are called blink. So we've got our C source code. That's a temporary file from the text editor. That's the kernel object. That's the one we want at the end. That's the one we insert into the kernel to run this module. We've got a couple of intermediate files, actually 3 intermediate files here, that are built during the build process. Blink.o there is the one we identify in the make file. It's a compiled version of the module, but it's not linked to the kernel yet. And long story short, the thing that most people are asking is, how do I actually build my module? And the answer is, you change this to the name of your module. I think there's one in here called frog fs2. Frog fs2.c. This is a demo from somewhere or other. I didn't actually write this one. That demonstrates use of the proc file. So then if we type make, we'll go ahead and try to build that one we just built. Now that particular one doesn't build, and I haven't shown you that file, but that's how you would attempt to build one at least. So if we want to go build the blink one, which does build, just change that to blink, run make, and it's built. So it's in some ways it's easier than building a regular program. The reason it seems complicated is the make file is covering a lot of stuff up. What make actually does here, the targets here, both all and clean, both called make again, and they go ahead and build it in this directory lib modules followed by the name of the kernel that we're currently running. That command shell uname-r runs uname-r on the shell, which returns that string, which is the version of the kernel we're running. So that gets inserted right there, and then we have build, and we have m equals, this is the current working directory, pwd. We look at this, echo $pwd. That's where we are right now. So that's where the module is going to end up when make runs over here, and then we're going to build a module. So if you look at that make file, it's somewhat more lengthy and varies a bit from one kernel to the next. Anyway, so we want to build this one that I was just showing you. So this 430 examples. I think I called it netgraph.c. Okay, right here. Okay. So there's the module there, and I don't think it's going to build. Okay. So yeah, we're missing that one part there on request IRQ. So let's take a look at the request IRQ function. If I put this here, we'll just use it right here. Okay. So that piece that's missing is the actual IRQ that we want to request. We've got all the rest of the pieces of this thing on here. Now so actually, let's go ahead and request IRQ1. Then netgraph.c. Okay, so we put 1 here. 1 is the IRQ we're looking at for the keyboard. So I put 1 there, and we should be looking at the keyboard's IRQ. Okay, it built. So let's go ahead and insert it. Okay, so it's inserted. The computer is still working, so our addition to the kernel can't have been that horrible. You never quite know on these. Okay, so let's go to proc, and I think it makes a file. Oh, I forgot what it's called. Let's look at it. So when you make a file in /proc, you're using something like this to build it. And so we're going to create an entry in a proc file system called netmon. And then probably the really important one here is this PFO. That's our file operation structure, and it's got read set to read proc, which is this function right here. So we're going to make a file in /proc, and when somebody tries to read from the file, what we're going to do is run that function, which is going to give us the value of tcount, which should be increasing every time we get an interrupt on interrupt number 1. So netmon. Okay. Now, it had one issue. Oh, does it change there halfway through? So it's printing out 159 repeatedly, and we got to 160 all of a sudden. That's actually when I pushed down the control key, and a moment later I hit the C key as well, which stopped it. And so let's go ahead and we'll put that up here. Okay, so there's running. So then down here, I'll start typing. Actually, I should type in something bigger. There was once an elephant that liked to eat walnuts, but it had trouble finding them. Okay, so you see how it's continuing to increase there. Now watch how fast it increases. So we're up to 404. So I'll keep going there because it didn't live near any walnut trees. See how it actually goes 2 per key? Rubbish period. See that? So it had to order them on Amazon using Alexa. Anyway, so you see it goes 2. So it actually stays even. Here, I'll push down a key for a moment.
Is it 2 calls because of the pressing and then the releasing?
Exactly. You figured it out. Good job. Yes. There's 2 interrupts issued, one for pushing down, one for up. And if you think about it, there has to be, because the computer knows if your key is down or not. And so it has to have been interrupted once for the key to be down, once for it coming up.
Makes sense.
Yeah. That also makes it sound like you're typing really fast on this particular keyboard because it clicks both directions.
Old-fashioned mechanical.
Right. Okay, so lots of interrupts from that. And so naturally, if we use the USB keyboard over here, we shouldn't see anything more.
You know, it's strange that so it handles the USB signals, but it's not interrupting this processor at all.
Not on IRQ1.
Oh, okay.
So it's got all these interrupt numbers. So the USB controller has one of them. And we can probably figure out which one.
And it's probably on another processor too.
It could be. Okay, so if we the count here for interrupt 1 will be higher than ours because we were hammering away on interrupt 1 long before I actually inserted this keyboard module and it started keeping count. So that's why we see like 2,915. Now, you notice that they're not strictly on one particular CPU. CPU 1 seems to get the bulk of the interrupt 1s, and that's not because of the numbers there. It's not like interrupt 2 will go on CPU 2 in hours. Okay, even though interrupt 0 seems to mostly fall on CPU 0. Okay, so the USB controller is probably one of these that has a pretty high number. You can see this particular interrupt down here, number 42. We've got 3,429 by CPU 0 and 66,635 by CPU 6. So that one appears to be pretty common. Sorry for everyone in the back. It's probably too low on the screen for you to see. Here, we can bring it up there. Okay, it has some commentary to keep following along, though. So at the end here, IRPCI MSI. MSI is the manufacturer of the motherboard, I think. Yep. Yeah. The same board as that one, MSI. This is not a good board that I'm waving around here. This is one where the PCI Express slot got pulled off accidentally. So it is junk, even though it matches the others. So the NVMe stuff on here, that's the device identifier for the solid-state hard drive. So it's got a high count because we've used the hard drive. What's that?
How'd you know that the NVMe correlates to solid state?
I remembered. But if you didn't remember, if you wanted to figure it out, you could do something like this. Type the mount command, you'll see which file system is mounted where. And so we should see a dev NVMe somewhere. I'll use the shortcut and let the computer find it. Right there. So dev NVMe. So then this is the identifier of which solid state drive we have, because I think we have more than one slot for these on this board. And even if you didn't, you see an identifier here. And then partition 2 is mounted on slash right there. Yeah. So the non-solid state one would be dev SDA something, and I don't remember if it's even mounted right now. Okay. So that's not our USB controller. Then you can see a few others for NVMEs that don't really have hardly any interrupts on them. And that's because there's not an actual drive on those slots. This one down here, NVIDIA, I would accept, if you follow up this line here, we've got 16,000 related to NVIDIA. That's our video card. And so it's definitely been in use too. Now these SND, HDA, and TEL, notice there's not very many on there really. 771 is not very many interrupts for one of these. So this is our sound card, but we haven't played any. I think they played a blink sound when I first logged in, and that's been it. So since we haven't used the sound card very much, we haven't accumulated. I keep talking about this like it's not very many. Do you know how often kids interrupt on average when they're around? I mean, this is not very many for a parent to handle either.
Depends on how old they are. When they're like, say, 2 to 6 and they're got 1,000,001 questions, well.
Yeah, that's true. It drops off a while later. Here, there's a sound card. So we were just looking at high ones. Now the USB might not actually be that high. So I got a bunch of PCI Express stuff here. Oh, here, USB 1, USB 2, USB 3. So we can try and verify that. It's actually pretty high on here, but if we just get those ones.
I was expecting to see a IR-USB-MSI, but.
Yeah, so you can see there's not a whole lot on there, but that means if I start actually causing some USB actions here, maybe. No, we still haven't found it yet. Anyway, if we hunt through there long enough, we'll eventually find it. Maybe identified differently. And it also may be one of those HCD ones in here. And you can see my PCI Express is continuing to build. So I call this one NetTrap. And the idea behind calling it NetTrap is it's fairly easy to find the network card and see which one it does.
These total calls that you're counting are just on the first processor, right?
Well, the kernel module here is counting all processors.
Oh.
The file there that we were looking at, yeah, it's got a column for each CPU.
Makes sense.
Yeah, here, I'll put this in here again. So if we wanted to take this and take that and put it into a file. Okay.
Oh, yeah, that's kind of crazy error there.
Control minus. Oh, here, we'll do this one. Close out saving. Okay, now I can use like control minus. So now it looks like a nice chart. It used to be that it would be a nice chart right away because we didn't have so many CPUs. These days, and I think we need a widescreen projector that just projects over that second screen over there too. But that's what it looks like. And actually, this is kind of an okay visualization, except that nobody except me can read those last ones. Maybe in the front row up here. No, okay. Okay. Yeah, you can. Okay. Oh, so here's something interesting. I'm going to make this bigger. So, well, okay. I'll tell you what it says. I'll make it bigger so you can see it says that. So I see this thing right here, the indecipherable text that only Matt there can read. That says netmon. And so the reason is we've just installed an interrupt handler called netmon. So that's where that identifier goes on there. So if we want to find the keyboard, what we need to find is the name there that has been associated with it, which apparently doesn't contain the word USB because the USB ones didn't seem to have that. Okay. But you notice the identifiers are really pretty short. Yeah. Okay, so there's IRQ lines and yes, and the request IRQ function and IRQ numbers and being a handler. Flags. Okay. There's a few other flags we can use here. We used IRQF shared. So what I'm talking about there is we'll just go get it somewhere else. Kmon. Okay. So right here, we said netmon for that. We said IRQF shared right there. So if we were to say IRQF disabled, that disables all the other interrupt handlers. Well, we've got ours there. Generally considered to be bad form. So there's a couple other versions here. IRQF timers that we're expecting an interrupt from the system timer, for example. IRQF shared is really pretty universally the one that everybody uses. Just want to show you that there are a few other possibilities in there. So yeah, we don't necessarily want to be in a random pool or anything like that. Let's change this thing to IRQF disabled. I risk losing the ability to use this keyboard, but since the USB one's on a different handler, we'll be able to take the kernel module back out and get our keyboard back, even if I make that mistake. And you know, and all this stuff, worst comes to worst, just turn the computer off and on again. Then it's better.
Yeah, because the module won't be there, right?
Yeah. IRQF disabled and declared. Oh, did they remove it? That could have happened. Disabled. Disable. That's spelled right. I think it might be gone now.
Yeah.
Sometimes they remove this stuff. There's something they removed that has been removed so that people wouldn't use it, but that wasn't this. But on the other hand, last time I taught this class, I think I was doing this stuff on a different Debian version with most of these things, and it was still there. Okay, well anyway, doesn't work now. Cool. That's probably fine. Okay. Oh, you want to see another bad idea? Okay, so we got this interrupt handler right up here. And so we want to finish this interrupt handler fairly quickly. So if we said something like this, for example, this would be a bad idea. We said size t sum equals 0, and then we said for n I equals 0, I is less. Let's not use an n. Let's use size t. Size di is 0, I is less than 2 raised to the 63rd power, I plus plus, and I'll put a nest these. And so this one will have j. So now we've got an interrupt handler that's going to take a really long time to run, actually. And we'll say sum plus equals I. Hey, we can engage the floating point unit here. That'll take longer to run. So let's do this double. It's more appropriate.
Okay.
Okay.
You're gonna need to change. No, you don't need to change the size. Jeez, never mind. Never mind.
Nah, that's fine. Okay, let's see what happens. Oh,
It
yeah.
tells you no.
So, well, it's objecting to the way the for loop is set up. So, prior to C version 99, you couldn't declare a variable in a for loop like this. After C99, you can. And most people that are programming C in this room have been doing it since 1999. Anyway, so the historical curiosity here. Let's set them up like that. Now it does mean that the scope is different. You see, when you do it this way in C99 mode, you actually restrict the scope of the variable to the loop. Right now they're not restricted to the loop. I and j still exist after the loop is done. If you really wanted to have the old behavior, of course, you could restrict the scope by saying that you're going to insert an extra scope just like that, and that would be fine. And if you want to make your code look weird, you can even put it there. Like there's something to do with that double sum.
People would be like, what is going on here?
Anyway, it'll work fine with these extra brackets here. It's just that it restricts the line of the scope. So I and j aren't here. Here.
Oddly enough, in Swift, there is a step where you ended up doing that after a declaration, and it's really weird looking.
Some things have some kind of like using map, and then you can down here you're using the math library or something like that. And C doesn't have that. Okay, so let's go ahead and build it. Okay, mixed declarations in code. Oh yeah, we did that. So the place we did that was here. Good point. Can't mix declarations in code. That would be bad. You gotta put your declarations first, code second. Okay, now we've got this function POW. I guess POW, I don't know if we can say include math.h here. Normally you don't use a lot of like regular libraries inside these things. Yeah, no. So let's say 2 raised to the 63rd. We could say 1 bit shifted over by 63 places. That won't be quite the same thing.
That's kind of weird.
Yeah, it's kind of weird.
But you still didn't remove the other POW.
Yeah, you're right. So that's still positive. Hopefully I did that right. Bit shifts are one of those things I don't do often enough to always get it right on the first try. Okay. That's what I'm saying. It's not going to get right on the first try. Okay, so there's a problem there. Left
Expected
shift
expression
with,
before double.
size t. Oh, it's not considering this to be a size t. There. A size t is 64 bits. It's a default into an int. And you can't bit shift a 32-bit integer over 63 places.
It's also saying there's a problem with that double.
Parenthesis, expected parenthesis, closing.
Or numeric.
Did I mess up the parentheses somewhere? No. No, that's just not working very well. Okay. So 2 would be to the 32. So that would be 1, 2, 3, 1, 2, 3, 1, 2, 3. That's about 2 to the 32. That's about 2 to the 32. So mine's about 2 to the 64. Is that? I do? Do I? Oh, was that the whole problem? Probably. Well, yeah, because it's a size T. Okay, well, there's still a problem there with the other one. Okay, we'll finish it. Okay.
Define big.
I'll go ahead and take that, and that will go there, and we'll make that one into a size T, which should take care of making it 64 bits. And then it's typical to put a parentheses here inside a macro so that it doesn't mess with anything like it might otherwise. And then we just say here, big. Same thing here, big. Okay. I successfully managed to write a large number.
Yeah.
No.
It's not like that.
I expected parentheses before size T. I don't know if it's like am I converting a static int?
I don't think so.
I can't do that, Dave. Not X, B.
Big equals B times B. That's funny.
Oh my god.
Expected expression before double. Oh,
I tried to point that out to you, but
you've been trying to point out gently that I should be using a C-style static cast instead of casting it as a C-negative. This is C++. Yeah, you're right. That was probably the entire problem all along. Because I did the same thing with size T in a whole bunch of places. Okay. Well, oops. So let's go ahead and insert this one. We got to take out the old one. Oh. Well, apparently there's a bug in the removal process.
You killed it.
Yeah, entire thing's down.
Good job.
Got to turn it off and then on again.
Oh, that was good.
I have to look at the removal process. So it happened as soon as I tried to pull a module. So probably there's something wrong with the removal. It might be that we identified the function wrong, or maybe the function has a bad memory address in it, or something.
Could it be because it's still running?
What's that?
Could it be because it's still running?
Like it removed the interrupt handler while the interrupt handler was going. Well, it can't do that because if it's busy being interrupted, it won't be pulled at the same time. It should be okay there, I think. We could probably undo that. We'll hope that's not it. Okay, there we are. We're back. Okay, so net draft. Oh, came on. Okay, so let's take a quick look at this thing before we throw it in. Oh, well, here's the problem. So our cleanup routine here, we say remove proc entry and get rid of our proc entry, and we get rid of the module, but we don't ever actually stop using our interrupt handler. So we need to remove our interrupt handler, like not request that particular IRQ. Okay, but I actually want to test this. Well, if I test it though, I'm not going to be able to get it back out. So free IRQ, that's what we want. It's the same thing in reverse. It has less parameters. So it's not probably in man pages, but we can find the documentation right here. It takes an IRQ and it takes a device identity for it, which I believe can be 0. And so we just have to call that and we should be good. Okay, so Q, IRQ1, and we'll just give it a null. I think that'll be okay. Okay, so hopefully that won't crash it. But of course, you just put this lengthy loop in the interrupt handler. Now, the only thing I have to do to make the loop not run is not touch any keys. And so we should be able to get this thing in and out safely. And if not, we'll just turn it off and then on again. Okay. Okay, so it's in. You know, that actually is responding fine. So it's, you know.
Huh.
I'm surprised it's okay. Now, that said, we do have like 12 cores on here, and it's possible that the optimizer might have deprived us of our loop, too. Because the loop doesn't actually do anything. And if it notices, it'll go ahead and take out the entire loop.
Interesting.
And I'm not sure what the default optimization parameters are for the kernel, but it's probably not debug mode. Okay, let's test our other thing. Okay, we had an input-output error. It's on the bottom, but nobody can see it down there. Here, I'll move it up. Uh-oh, what's... My keyboard doesn't work.
What have you done?
He broke it.
Okay, so if I go ahead and cover up that one, bring it up here. So you can see we have this input-output error at the end of this thing. The reason we got an input-output error is because we were reading from this proc file, and then we removed the module that generates the entry. So then the file ceased to exist. And so then we were trying to read from a file that didn't exist anymore, and that caused an input-output error. Go figure. Okay, the other problem. So we freed the IRQ, but it looks like perhaps we've unintentionally actually freed the IRQ from the other handler that normally handles it. So I'll just leave the computer as well, except that we're going to try and
You think the
monitor.
file would still exist, though, because it was writing to it. Why would the file cease to exist? Is it
Well,
like a temporary file that
there's no
actually-
more file to handle there's no more module to handle the read on the file. So it can't read it. If it tries to read it, you know, the answer inside the kernel is there is no such file. As far as the program is concerned, the thing is still open. So that's why the program receives an input-output error, because the kernel's telling it this isn't even a file. Now, normally you can't remove a file that completely when it's open. If you had a regular file in a file system and you delete it, the file will actually stay present in your file system until all the programs using it have closed it. But this is a different case. This is more like if you were using the file and then you unmounted the device and removed it from the computer.
Well, it's kind of like you trying to move a file that you have open with something else. You'll get an error.
On Linux, it'll be okay.
Whatever.
Yeah.
Ran into that before. Go to move a file and then I get this error because I have it open in Notepad++ or something.
Yeah. Okay. Typing then. The editor there is not responding to my typing. The window manager is happy with it. Isn't that odd now? Can I close it? All it for? No. Wait a minute. Now, okay, this is getting worse. Now I can't open new windows. I can still switch and do
Switch
stuff.
between what you have but you can't open.
I can't open a new one. No. What if I just hit Control F1 to switch to a virtual terminal, and I think I've lost everything now. I don't have a mouse either. Okay, off and on again.
So weird.
So your module just slowly killed everything.
Yeah, it did.
Like, oh, you're using that? Here, let me kill it. Oh, you're using something else? I'll kill that too.
Well, this is part of the fun of kernel development. When your program has a bug, your whole operating system has a bug.
I'm kind of curious how it did that.
I was going to put it back in and see if it started monitoring traffic again. I didn't really expect the PS2 keyboard to start working again, but I thought maybe it would start monitoring for interrupts and it would record interrupts, but the keyboard wouldn't work. That's what I was getting ready to do. And then I started making the file to show you can move a file that's open. And then, yeah, everything stopped. Okay. Wait a minute, wait.
Oh my.
Okay,
Uh-oh.
well, this is interesting.
Dude, bro.
This one works.
Oh,
Oh, it does work now.
This one works now?
Okay, well, this keyboard works now, and it didn't used to work. And this one, does this work too? Great. How exciting. Okay. Anyway, so okay, let's see where we are real quick. I've got 20 minutes here. I got to finish showing you things that I'm supposed to show you. Okay, yeah, disabling things. I did try this time, and it didn't work. But we did manage to get rid of the other one. This is a different mechanism I was talking about that's not around anymore, so don't really worry about that too much. Okay, yeah, I think we're mostly at the let's try things. Okay, so the network, the module here went out, okay, kind of, but we had some trouble a little bit with it disabling this particular interrupt. Why does it play pause? Oh, because there's the scroll on. That's fine. Okay, so let's go back to the KMod here. Let's drop. Let's see. Oh, regular gun. Okay. Hey, it works now. Everything's actually pretty good now. Good. Okay, so we caused a problem in the kernel last time and started blinking the first and started blinking the lights. Now that we said free IRQ and we freed it, it seems to actually disable the keyboard. But I really do want to try throwing this thing back into kernel, hopefully before everything goes sideways, and see what happens. So let's try it. Nettrap.c. Okay. Or .c. Okay. Okay. So, proc netgraph, or netmon. Okay, so that works fine. And so then if we remove it, okay, oh, shoot, this time it broke. That one doesn't work, this one doesn't work. I got lights blinking, indicate that something is quite messed up, and nothing is happy. That's odd, because that's actually a different result than we got last time. So, remember when I said that the free there, we could probably leave the device ID at 0? I'm kind of thinking that maybe we can't. Oh well, off and on again it goes.
So what you're saying is with kernel development, you're going to be turning your computer off and on a lot.
Yeah, some people prefer to do it in a virtual machine just for that reason.
Yeah.
I can see that.
Okay, so once it comes back up, so we made an IRQ handler great. Removing it didn't go so well. Removing it isn't actually a very common thing to do. Most of the time you don't pull an interrupt handler because that would mean you're pulling the device driver for some kind of device that, you know, usually you don't change the hardware configuration much while you're in the computer. And plug and play only exists so far as well. Plug and play, the reason that that exists is because of those ISA devices where you had to configure the device using jumpers. And so now that those are gone, we don't really say plug and play very often anymore. I don't think these boards even have a jumper on it. This is the motherboard. Sometimes there's a clear CMOS jumper, even on kind of modern ones. But I don't see one on this one. It's probably got a,
Nice
no, it says
motherboard.
switches.
Yeah, nice
Yeah, button
motherboards
key
have
push.
dip switches or buttons.
Yeah,
Yeah.
It's, they've kind of just slowly been modernizing those.
Right. I don't think I've set a jumper on a computer in a decade. Still have some around somewhere. Okay, so anyway, what plug and play meant was you take your device home and you take it out of the shrink wrapping package, and then you take it out of the cardboard box, and then you take it out of the styrofoam, and then you take it out of the anti-static bag, and then you take off the rest of the packaging, and then you put it in your computer and it starts working. So it was very different than having to scratch your head with IRQ problems for a long time. So plug and play was great, but plug and play did not mean that you could plug and play it while your computer was on. There's servers where this has been designed in. The hard drives on a software are hot swappable. You can pull one out and put one back in while the thing's running. Sun servers that cost a whole bunch of money used to be able to do the same thing with processors. You can pull one or more processors while it was running.
Wow.
Couldn't pull them all, but you can pull some of them. Most PC hardware is not designed to hot swap. And so most of the time, you're not going to be pulling out your NVIDIA graphics card, pulling out the NVIDIA kernel module, putting in an ATI video card, and putting in the ATI kernel module.
Wow, it's not.
Well, it's on.
I think I saw something about PCI Express hot swapping. It's an actual thing that's being introduced.
It is, yeah. Servers have had the capacity to do that for a good while. Anyway, so I think we found our device ID. We could probably pull this thing out.
Because CMOS is so sensitive, it's just a scary idea.
Oh, yeah, pulling something out while it goes. Yeah. Oh, and then we got our loop that I think might have gotten optimized out since it doesn't actually do anything of any lasting consequence. What if we take sum up here and put sum down there and then report sum down here? Since everything's fine until we pull a module, we should be okay putting that in there to see if that works.
Which also forces our loop to not be optimized out.
Yeah. Okay, so now this cleanup thing down here, I'm not exactly certain what to do there. Oh, you know, I might know what this is. I think we might need to put the IRQ handler here. I'm going to guess that because I think I might remember that.
Yeah.
SSE register return with SSE disabled. Isn't that a good one now? Okay, so SSE is a instruction set for Intel processors that AMD uses too now. And so apparently we're trying to return something in a register that's not enabled. Wasn't that interesting now? So what if sum wasn't a double? Oh, well, we said that I is a double. Okay, so now we have a format error, and I don't think we can optimize the loop out. Now that might be a good indication that actually it optimized the thing out before. The SSE registers may not be available in the interrupt handler. We could check and see. So if it was the way, if that was happening because this was a double, and we put it in here and we say double, and we say double here. So now we're going to have an error right down here. So actually we can't do that at all. So we shouldn't do that. Sorry, thought I was onto something, but I don't think I was. Okay. Okay. It still has the you can't remove it problem. But we can at least see what happens while it's in. The keyboard didn't respond. Hey, this one does.
It did.
Uh-oh, the computer seems a little busy. I think what happens is it will respond about 6 times. After that, all 6 processors are busy with their giant loop.
Yeah, I was gonna ask if it was a loop that was really stalling.
Oh, there it goes.
Hey, cool. Okay, so it should respond normally to this keyboard. Or not.
You were there, sure.
It actually did process those ones eventually.
Oh, that's great.
So I'm not sure what interrupt this keyword's on, but it appears that the works are still gummed up, having an interrupt handler that runs a very, very long loop. Now, that said, it did finish. So what if I start typing something long? That's good. When I press enter, are we fine now? Well, that's got an apostrophe in it, which is a single loop. Cool. Okay, so the computer seems to be pretty good now. I think all 6 loops finally finished. So with this keyboard, I get to press the keys once, twice, maybe, I don't know. It works fine with the other keyboard. My keystrokes may actually eventually appear once the loop finishes. It could actually take a while. Okay, so this is, what's that?
I said, congratulations, Seth. You've successfully made a modern, really fast computer behave like a computer from the late 80s.
Well, let's use the modern USB keyboard. One with the sticky spacebar. Yeah, you're right about the spacebar. I saw 2 there one of these times. It's not frequent enough to really predict it. It's just that sometimes it happens. The keyboard's actually kind of horrible. Okay, so I don't know what's up with the keyboard there. I just pushed the number lock and it didn't appear. I just pushed the number lock on this keyboard and it did appear. The no lock status is the same, by the way. It doesn't have independent one per keyboard. I realized that what everybody who's planning there is to take a keyboard like this and cut off this section and then have one of them operate with numlock on and one with numlock off, and then glue them end to end so that you have like the keyboard that has both ways at once. And then maybe do the same thing with caps lock, but it's a per system setting. So that won't work. Okay. Okay, so what else was I say? Oh, am I not? Oh, I just said I don't have any other windows. Except I just told it to start the web browser. Yeah, so something's taking a little while on there. It's not particularly happy with the super long loop running inside the kernel. I probably pushed too many buttons on the other keyboard, like when I was pushing numlock and things, and gummed up the works again. It'll be better eventually, but it won't be better if I pull out this kernel module.
Then it'll just
Oh,
die.
wait, I put the thing in it to see if it would. Remember that?
Well, shall we try to get it out of there?
Yeah, we should. So we'll start Google Chrome. So I sudo rm mod that trap. Okay, now RM mod itself might take a while, since everything takes a while right now. But it might come out fine.
We have 9 minutes to find out.
Yeah, I might turn it off and then on again. And we can RM mod it when the computer is actually working okay.
No, just leave it all hung up like that for Nina.
Well, this keyword's fine, the close keyword. Okay, off and on again. Okay, so keyboards, yeah, they can cause problems. We're kind of doing a tour of what happens if here in the kernel, and so we haven't been being particularly careful. That said, I didn't intend for this thing to kill the computer when it's pulled, so that is a genuine bug there. Okay, once this thing comes back, if it comes back, let's see if we can actually pull it successfully. Out it comes like a bad tooth that we put in. Don't mean to make us sound like psychotic dentists or anything.
You'll be back for another visit.
Yes. I actually have a missing tooth that at some point it might be good if it was replaced with an implant. But that's always a concern there. Okay, so the Kmod. Let's go ahead and get rid of our loop here so we don't mess things up more than they have to be messed up. I'll just get rid of it, including big. Okay. There, that's all restored, and then that just goes away. Okay. Okay, so there's a new one. Okay. I think I spelled that wrong. I'm typing over a different keyword. Okay, works good. Hey!
Yay.
Cool.
Actually removable now, huh?
Okay, so I can't remember why this is the case, but the dev down there is actually the address of your IRQ handler. I thought I remembered that, and apparently it works. Does that mean I was right? It's not a definite proof, is it? But whatever number this represents does seem to make this thing work now. Oh, watch the computer stop responding in a moment here.
It means you found a way to kind of make it work potentially.
Yeah, that's a little bit different. Okay. That works good. That works good. Okay, notes today is September 27th. Okay. Okay. So we tried it, and okay. So a reminder here on system calls. System calls do interrupt 80, and so if we look through the interrupt table table there, we should be able to find it. I think I did a perfectly adequate job of saying these things a dozen and a half times, so that's fine. I showed you a lengthy top half of interrupt handler, and it was really, really bad, so that was good. Now ours is a very lengthy top half for the interrupt handler. You don't really want any kernel code that runs that long, let alone an interrupt handler. A little bit of an extreme case. Yes, we saw that it can give up the works. Remember, not everything is actually multi-core. ARM processors are increasingly multi-core. Oh, here, we'll just do a poll. For those of you that have a phone and know how many cores it has, how many have a phone with more than one core? Raise your hand. 8. 8, okay.
Same.
How many know that they only have one core in their phone? Okay, so our unscientific poll here suggests that phones typically have more than one core now.
Oh, the newer ARM,
Yeah. And so I guess ARM is up to the point where most people are carrying around a multi-core ARM chip if they're carrying one around. So there's not a lot of single-core systems left then. That used to be my big example. All the game consoles have gone to a whole bunch of cores. Computers will have gone to a bunch of cores. Probably embedded microcontrollers and home routing boxes are up to multiple cores these days. I don't know.
Raspberry Pis, 1 core.
Yeah,
I do too.
Good example.
Yeah, I've got one as well. So that's why I used to use ARM as an example. I don't want to crash it because it's in my chicken coop and I can't turn it off and on again. And if it goes crazy, it'll open and close the door a few times.
But yeah,
Be dead one of your chickens.
Sitting out there watching it. And
It opens really slowly. They always notice.
it'd be funny if it did move really.
Well, it's connected to a garage door opener that moves slowly, so it actually does a switch direction a bunch of times.
So
Ending up in a semi-random state.
So the door would sit there and dance.
Yeah. It does that during boot up, actually, if I restart it. Because it does a polling sequence to see what's connected to the general purpose I/O pins. And it doesn't find anything it recognizes, so then it gives up and I get to control it manually. But I haven't figured out a way to disable the trying to figure out what's connected process. I probably have to go and edit the kernel to stop that. I was looking for like, you just don't insert some module or other, and I didn't find one.
I just imagine while that's happening, all your chickens are in one corner except for one who's trying to get through the door while it's doing that.
It doesn't get rebooted very often. So the top versus bottom half, really pretty universal. My examples from NetBSD with the device driver. So I guess that's that. Okay, so practice problem. I didn't put one on here. Sort of forgot. So you can kind of see what we're doing here with modifying this thing and whatnot. So I would say use netgraph to count say actual network interrupts, or maybe video card interrupts. That might be a good one. Depends on what system you're testing it on, and the IRQ can vary. And so you'd have to look in the proc interrupts and figure out which IRQ it is, and then insert this program for that particular IRQ. And of course, if you mess things up, it'll mess up your video display, but you just turn the computer off and then on again, and you're good.
And what about when you're virtualized? So that's generally how I do things.
Should be fine. It'll have it probably won't be in
Like
NVIDIA
a generic
module or
assignment.
HF. Yeah, it'll probably be an Intel one of some sort. But yeah, same process. You find where it is in the proc, and it proc interrupts. You count that file and figure out which one's the video card and insert a handler for it. There may or may not be some problem with the video card not wanting to share. Potential complication. Yes, so
I was
should figure it
curious
out.
about that. Be interesting just to mess with it, just see what it does.
Yeah. Okay, so that's that. So if you want to practice something for the test, C programming, and of course this module stuff, anything in there is pretty good to practice. I have a lab that has practice stuff, and I haven't assigned it this year, but I can put it up there as a practice thing to get ready.
Yeah, and there's also the little challenges you put at the end.
Oh yeah. Well, that's only for the last few. It's a new thing. I haven't heard that anybody actually did one yet. Maybe did that one yet?
I haven't, but you know, I will only do 90 for the midterm.
Okay.
I was going to, but I started your finance first.
Oh, okay.
Yes, it's
Yeah.
has priority.
Yeah, it does, because it actually counts for points. These don't. Well, they might count for midterm points, maybe. Yeah, get more from them.
Oh.
Well, because if you do better on a midterm, it's only indirectly counts for points.
Have you started grading anything?
No, and I need to. I keep just guys sending us.
I'm just asking for your own sake, you know?
Yeah.
If I would love
Yeah, because it's going to all pile up. I realize that most people actually know what they got on project one, since they know if it worked or not. Yeah, hopefully one of these days. Okay, well, I think that's it. So have a nice weekend. See you all Tuesday or other times.